All right, ready for another big day of programming paradigms?
Yes.
And it sounds like some of you guys have Scheme already downloaded and installed. Are we good? And were there any questions? Did you say you had a question about setting up Scheme? Some people are asking, where are you supposed to download it from? It doesn't matter where you download it from. You can download it from Europe. Everything's, it's the same software, but just to decrease the traffic on the internet a little bit, you can download it from the nearest mirror site. And then actually, maybe what I'll do now is I'll go to a demo mode. Okay, so here's our demo. Now, unfortunately, my screen capture software crashed during the lecture, so I'm having to do this offline, so it will not be quite as spontaneous as the original, but we'll forge ahead anyway. Okay, so now first thing that we want to look at is how you can test Boolean conditions. So here's an example of the less than function. Remember, everything in Scheme is a function, and functions return values. And so this less than function returns a value which is either true or false. So suppose we ask less than 2, 3. Right? So what do you suppose is going to happen when I press return here? Well, is 2 less than 3? Yes, it is. So we see here that what it returns is this £t, which stands for the true constant. And of course, if we ask, there's also a greater than 2, 3, that's 2 is not greater than 3, so that's going to return false. So there's the false function. And furthermore, these constants each evaluate to themselves. So do you remember in the same way that, remember when we did like 8 and press return, we see that integers evaluate to themselves? Well, these constants, £t and £f, you see £t evaluates to itself and £f also evaluates to itself. Now, of course, it doesn't, where do you use these conditional functions? You use them in if statements. Now, where was I? Oh, so the question is, with what does a function do?
Returns a result. Or processes information to return.
Well, that is the Scheme loop. That's the read eval print loop. But what about a function? The read eval print is the thing that controls the interaction in the bottom pane and the lower pane of Dr. Racket. But what does a function do? Yes, it returns a value. Okay? So a function always returns a value. Are you with me? Question.
What would you call it then if it's a function that doesn't return a value?
No. A functions always return values.
Well, what do you call something that just changes values?
No. That is such a good question. The question was, what do you do with a function that just changes a value but doesn't return something? You have asked a very, very deep functional programming question. And the answer is, in this class, when we do pure functional programming, we will never write a function that does that, because that's not part of the functional paradigm. And we're going to see how that plays out. That is a really good question. Does everybody follow what he was asking? The question was, what about a function that changes a value but then doesn't return it? In fact, in the procedural paradigm, what is that called? Called by what?
Reference.
It's called by reference. Are you with me? And we used call by reference in the procedural paradigm to change the value of one or two variables. And you remember the difference between call by reference and call by value. Okay? We will never do the equivalent of call by reference in functional programming, in pure functional programming. So now I ask again, what does a function always do? it returns a value. Are you with me? So now let's go back to our demo. So now what does every function do? It returns a value. So let's check out the if statement, the if function. It's actually a function. So now, here's our first example. If £t 5, 7. Now this actually elicited a lot of discussion in the classroom that I wish I could reproduce here, but notice that the if function has 3 arguments. The first argument in this example is £t, the second argument is 5, and the third argument is 7. And the way it works is, if the first argument is true, then the second argument is returned. Otherwise, the third argument is returned. So since £t is always true, this returns 5. And then we can say if £f 5, 7. So what this will do is, because £f is always false, this will return 7. Okay. So how does an if statement work in Scheme?
The same way it works in Excel.
Exactly, the same way it works in Excel. Oh, that was a good observation, because actually, truth be known, Excel, the way the functions work in Excel, that is functional programming. That Excel spreadsheet, formulas, those always return values, and that's why that is a really good practical example of functional programming. So how does this if statement work, you guys? There's, first you have the if, then you have a Boolean, then you have what? Yes, you have 2 things, one of which will be returned depending on what? Yes, on whether the condition is true or false. So you have what gets returned when the condition is true and what gets returned if the condition is false. Now, are you with me on that? Is everybody clear? Does everybody see how that works? Okay? Yeah. Oh, it's the £t and the £f.
What are those referring to?
Oh, those are constants. That's like actually typing true. That's like saying £t is like, it would be like, true is a constant. Yeah.
So in this, would you be able to replace £t with like?
Generally, that's what you, yes.
With like something that would actually be comparing two values?
Yeah, oh, let's do it. If, yeah, so let's do what you said. So if what? This is normally how you do it. If what? Yeah, if less than 2, 3, 5, 7, okay? So now, all right, now actually, what about the read eval print loop? Now, you guys, when I press this, what's going to happen? Well, I know, but it's going to be read eval print. Now, so can you deduce what? Yeah, let's go ahead and do it. 5, right? Okay, but now look, what does the eval do? How does eval evaluate a function? Well, look, it reads the if. Are you with me? Then what does it do?
Evaluate the condition.
Well, it reads.
Oh, then it reads the condition.
It reads and it has to evaluate. Not only does it evaluate the if, it also has to evaluate the what? The less than 2, 3. Are you with me? So each one of its parameters is also evaluated. And then after it evaluates those parameters, then the outer one. And those evaluations can be nested arbitrarily deep.
So the innermost parentheses is always evaluated first?
Yeah, yes. The innermost parentheses is always evaluated first. Chris, did you have a question?
Yeah, it may be necessary, but I'm still kind of confused on why the true returns 5 and the false returns 7.
Because okay, let's take a look at the board. Look, all if statements are like this. If condition, true part, false part. Okay? So this is always this is the shape of an if statement in Scheme, in Lisp. All right? And the way it works is this condition is a Boolean expression, right? And if this is true, true part gets returned, and if this is false, the false part gets returned. Are you with me? But now look, if in this particular example that we had, if we put pound t here, this is true always. This is the true constant. So because if there's a pound t, this will always get returned. This is a constant. You see what I mean? But it's a Boolean constant. It's not a numeric constant. And true pound t is always true, and pound f is always false. Yeah.
Can the true part or the false part be a function?
Absolutely. That's usually it is.
Okay.
Yeah, and this can be all. And what is a function? Parentheses, function name, and arguments.
Well, I guess what I was trying to think of is like there on one of the most recent lines, you have the less than 2 or 3. Could you make that a variable so that you could have less than or greater than?
Yeah, yes, we're going to have variables.
Okay.
Yes. In fact, yes. In fact, we did that. We did remember when we defined the area, and we had the parameter. The variables are always the parameters. They're always the parameters. Remember how we had lambda x, and then we had times x, and then when we did that with 5.
I didn't mean the number values as variables. I meant the actual function. Like, could you have the variable be either less than or greater than?
Not only can we will. In fact, and that just, boy, you're asking really good, deep questions about functional programming, because in functional programming, the function itself is a list which can be manipulated like data. It is, yeah, it is. This is not just, maybe some of you yesterday were thinking, oh, this is like a little calculator. No, there's some deep stuff, function theory stuff behind this. And we will, and you'll see, it's going to be really slick. It's really nice. It's very nice. Okay, now, so is everybody with us so far? All right. So now let's go back to the demo mode. Okay. So now, of course, you hardly ever use an if alone in a by itself on the command line. So what we'll do now is we're going to write our first function that has an if statement in it. And what we're going to do is we're going to replicate a function that's already in Dr. Scheme. So namely the absolute value function. There is a function called ABS, and it works just like you would suspect. The absolute value of 7 is 7, and the absolute value of -7 is also 7. So now what we want to do, and of course there is no function called myApps. See, myApps is undefined. So what we want to do is we're going to come up here to the top pane of Dr. Racket, and we are going to write our own myApps function. Okay, so here we go. And how do we define a function? We always start with define myApps. Okay, and this is really not as interesting without the classroom participation, but we'll just forge ahead. LAMBDA lambda, and how many parameters does absolute value have? It has 1, right? So we'll name it X. We can name it anything we want. And so now what do we want to return? So now here's the question. Can you figure out what we have to write next? Well, I mean, it depends on what X is, doesn't it? If it's negative, then we want to negate it. If it's positive, we don't want to do anything to it. If it's negative, we want to negate it. Now, do you remember how to negate a number? Here, let's go down here. It's going to give us this yellow bar, but we can forge ahead anyway. Do you remember how this worked? If we say negate, if we have the function, the negation function of 7, then See, it's giving us that warning. But anyway, if we negate 7, it's -7, and if we negate -7, it gives us 7. So what do we want to do here? We either want to negate or we don't want to negate. So let's do if. So there's our if. And now what is our condition of our if? Well, let's check to see if it's less than 0. If less than x, 0. So if x is less than 0, that means it's negative, and we need to return the negation of it. So what comes next? Parentheses, negate x. Otherwise, return x, just unchanged. Okay, so there's my apps. Let's compile it. Looks like it compiled okay. And now let's test it. We will do my apps 7, and sure enough it's 7, and my apps -7, and sure enough we have written our own absolute value function. All right. Now, the next demo is going to be our quilting demo. Now, in order for these graphics programs to work, the instructions are on the web page. You have to install a package. Let me go over to our web page here. Let's go over to our web page. And on the web page, I have given you a copy of two packages, two things that you need to do to add to Dr. Scheme, Dr. Racket, in order to run these graphics programs. The first one is called concabs.plt. Concabs is concrete abstractions. That's the author of our textbook wrote this. And if you click on this big old long, encoded .plt file is available, and what you should do is you should copy this to your to the directory where your doctor's racket is located. See up here, it's a .plt file, and then there's instructions on there on how to install it. Then once you install it, you only have to install it once. Once you install it in your local directory, then you don't need to do that again. And the other thing is this quilt.txt. So I've also given you a copy of this quilt.txt. Now let me show you here. This particular line right here, this require, this is not in the quilt file that's available on the website from our author. But you need to have this in here in order to run the programs anyway. So I added this line. So if you follow that link to our web page that I just showed you, this line is in here because you're going to need it anyway. Otherwise, if you get it from the web, you're going to have to add this line. So basically what you have to do now to run programs, the quilt programs, is let's just select all and copy, and let's go back to Dr. Racket. And now what we'll do up here is let's paste this in here. So this is all pasted in here. Now here's another thing that I have given you, is I put the three items up here at the top. You need to put your name here, the date here, the assignment here, and then here's that line that I showed you that I have added to the file that the author provided. And then what I want you to do is put your programming exercises here. So here what you'll do is you'll put, like something like, I forget the exercise number, but it's like exercise, 99.9A or whatever, blah, 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 And so that's where your exercise, and then they'll always be in the form of a define. So this would be like define whatever, okay? So that's where that goes. And now the only time you need to do this is whenever you're using these graphics programs. Now look here. Let's run this. Okay. So there, it all compiled fine. And notice that what he's done, what our author has done here, he's defined this thing called define test BB, define Nova BB, and there's some other ones. There's an R cross. There's some other ones. So look, if we just do test BB down here, it's been defined. So let's press return, and look at that. That's the little pattern, little graphics pattern. And this, what it is, you can tell right here from the name of it. What it is it's a filled rectangle, you know, and so, and then he's got, but then you have to define filled rectangle and so on. Okay, so, or sorry, filled triangle. And then these other patterns, and you know, you can look at how they're implemented later, but the main thing is that they're defined. That's all we need to know for this exercise. So let's take a look at Nova BB. Okay. So there's a nice little interesting geometric pattern. There's another one called R cross BB. There's the R cross one. That's the one that we're going to use to make the quilt out of. And then I think there's one called corner. It's just C-O-R-N-E-R, corner BB. So that's what the corner looks like. All right. So now these geometric objects have been defined for us up here in this quilt file. Okay, and now the question is, what can you do with these patterns? In other words, anytime you have a data structure or a class or whatever, then you always want to know what are the methods or what are the operations that you can perform on this. So there's two kind of like primitive or basic operations that you can do with these patterns. One of them is called stack. So check this out. Let's do stack, and we'll do R cross BB and corner dash BB. Now what do you suppose stack will do? Now you see the pattern for R cross and the pattern for corner. So what do you suppose that will do? And obviously stack takes two arguments. And look at what it does. Stacks them. And which one is on the bottom? Looks like corner BB is on the bottom, right? So they're stacked from the top to the bottom there, right? And I don't think this works for 3. I think, let's try it. Stack R cross BB corner BB. Let's try to stack Nova. I don't think this is going to work. Yeah, see? It says the expected number of arguments does not match the given number expected to given 3. So we gave it 3 arguments, so that didn't work. Okay, so stack, let's clear this off by running it. So that stack is one of them. Now here's another one. Let's take a look. Let's review what test BB is. And now what we'll do is, the other one is called quarter turn right. So that's QUAR, quarter turn right. And then we'll do test BB. And notice what it did. It did a quarter, well, it did a quarter turn right. Okay, so 90 degrees to the right. Notice that this image here is actually in a square. The whole thing is contained in the unit square, like this. And so when we turn it right, notice that this long side is at the horizontal midline of that unit square. Okay, and now obviously what you can do is you can combine these. You can nest them. Okay, so see if you can predict this. Quarter turn right, stack, test BB, test BB. Okay, and then paren. So obviously what's this going to do? And here's where we're missing a lot of good classroom interaction. But anyway, we're going to put test BB on top of test BB, and then we're going to quarter turn right the whole thing. So now instead of being stacked on top of each other, it's a row. Okay? And how about this? Stack, quarter turn right, test BB, and then test BB. Oops, 1, 2. Yeah. So what's this going to do? This is going to do quarter turn right, test BB, so that's going to flip it to the right. Then we're going to stack that one, and let's see, will that one be on the top? Did we say that one was on the top? Yeah, the quarter turn right one was on the top, and then the test BB was on the bottom. And now, let's take a look at the slide on the board. And then we'll come back to here and let's see, have you figured out now how to produce that pattern that we had on the slide? Well, here we go. Let's try it. So obviously you have to stack two things, right? But what are you stacking? You're stacking two rows. Yeah? So what you have to do is you have to make a row, and then you have to make two rows, and you have to stack the two rows. So here we go stack, and now what's the first row that we want to stack? Well, the first row that we want to stack is what? Quarter turn right of what? Stack R cross BB R cross BB. Okay, so now do you agree that everything from here to here is a row? And so what do we need? We need two of these rows stacked on top of each other. So let's just take this whole thing from here to here as the first row. We'll just copy. And so we're stacking those two rows. So now if we close out our parentheses here and we stack those two rows, what do we get? Ta-da! The pattern that we wanted. All right. Excellente. Okay, so now what let's do is let's move on to chapter 3. Or sorry, chapter 2. So this chapter is about recursion and induction. And now everybody here we know recursion, right? Actually, let me make a comment about our textbook. Our textbook is intended to be an introduction to computer science. So this book was actually written for like first year computer science students. And because we all have programming experience, we're just going to be zipping through this material really fast. We're not going to, it's kind of tedious to read because it's written for beginners. But so we're going to be going through this material really fast. So I assume that everybody knows how to program recursively, program recursive functions and procedures, and you don't need to like study every page of the book because you'll find that you already know most of this stuff. So tell me, what is a recursive function? It's a function that calls itself. And one of the very first examples that you probably learned when you learned how to program recursion was with the factorial, right? And tell me, so on this slide, what is the recursive definition of n factorial? Well, it's 1 if n equals 0, and it's what? N times n minus 1 if n is greater than 0, right? So you've seen this before? And so now the question is well, the point is, it's really straightforward to write a factorial function in Scheme based on this recursive mathematical definition, because this recursive part, this is n defined in terms of n minus 1 factorial. Right? So you assume that you can call this n minus 1 factorial is the recursive call, and then we multiply that by n, and then that's what gets returned. Is everybody with me on this? Okay, so here, let's do it. Let's try it. So let's go back to Scheme, and let's clear off our workspace here. And since we don't need the quilts anymore, let's just quit that. And now, so using that definition of factorial, let's do it. So, what is the definition of factorial? Well, we have to start with define factorial. Okay, here is lambda, and how many parameters did it have? 1, yeah, so we'll call it n because it's an integer. Okay, and now what's our base case? Well, yeah, I guess we could make it 0, but let's make it 1. Let's say if equals n1, then what is 1 factorial? What do we return? If n equals, oh wait, we need an extra paren here, don't we? If equals n1, so the first element of our if is the condition. The second element is what gets true returned if that's true. So if that's true, what gets returned? 1. Otherwise, what gets returned? So here comes the recursion. So what do we have to put here? Factorial? No. Factorial? No. Why not? Because what do we have to do to that factorial? We've got to multiply it times something. So here we got to put the multiply. See, this is Cambridge prefix notation, right? You got to put the operation first. This is a prefix notation. So we multiply. Now what do we multiply? Now I guess you could do it either order here, but let's do the factorial first. Factorial, and now n minus 1, right? So do we put n minus 1? No. Do we put n minus 1? No. We put what? We put minus n1, okay? And now this paren closes out that factorial. So now we want to multiply all of this times what? Times n. Boom, 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 boom. And that should do it. Now, does everybody see how we got that? All you guys out there in video land? Okay. Let's run this. Oh, looks like we didn't have any mistakes on the syntax. And now, let's go and try it. Now, this is really impressive. You're not gonna believe this. Watch this. Let's do factorial. What was factorial 5? You remember that? It's 120, right? But check this out. Factorial 10. Yeah, pretty good, huh? And watch this. Here's the one that was done in the book. How many cards are there in a deck of cards? 52, right? So how many ways is it possible to shuffle a deck of cards? In other words, how many possible permutations do you have in a deck of 52 cards? Watch this. Well, it's 52 factorial, right? Watch this. Factorial 52. Whoa! Check that out, sports fans. That is one big number. I dare you to do this in C++. Yeah? Because, I mean, one cool thing about Scheme is it has infinite precision integer arithmetic. It will just keep allocating storage, and the algorithms can do the arithmetic operations all automatically behind the scenes. In fact, I dare you to do this with any other system. Factorial, how big? 80? check it out. It had to word wrap. I mean, you could even do factorial 100. Look how fast factorial goes up. Can you do 500? I don't know. That's pretty big. Wow. And check out how fast it is. Look at all those zeros at the end. That's because there's a lot of tens, you know, in the factorial of 500. There's a lot of numbers that end in 0. Pretty amazing.
Yeah, I mean, you try to do this in C++ this easily. This is like infinite precision integer arithmetic.
How is that possible?
Yeah.
In Scheme. Isn't Lisp powerful? Yeah. And with that, we'll call it quits.